So we're going to do a few more examples of like the plots to just make sure it completely makes sense to all of us. Okay? To just refresh your memory, like what we talked about was if we have like a transfer function or a frequency response, we need to plot magnitude and the phase, and to be able to plot the magnitude, we have to like plot the magnitude on the scale, which was 20 times log 10 of the magnitude of h of omega, right? And we said, if we can write it in that certain form that we basically, we can see all the zeros and poles, then the rest is like pretty easy because we know exactly like how zeros and poles can contribute to the entire basically transfer function, right? The whole idea behind it was if I have a pole, it means I'm going down, and depending on like the typicity of the order of it, go down by like 20 times the order. And if I have a zero, I know the zero must go, depending on the order that I have, I go up to like 20 times that order, right? So let's quickly do like a very simple example to refresh our memory, then we can make it a little like more difficult to see how we can actually do it. So example, let's just say I'm given this h of omega, which is 10 times I omega plus 1, divided by I omega squared, plus times 0.1 I omega plus 1. Question is, I want to plot this, right? The very, very first step is to rewrite this and exactly what the zeros and poles are, right? So if I look at this h of omega, it's already written in that form. I just need to like play with it a little bit to make it exactly look like that function that we have. So let's rewrite it. Well, this constant 10 is just a constant. You don't have to do anything with it. The second term is already written in terms of I omega divided by z plus 1. So it is basically I omega plus 1. So I don't really have to do anything with it. This I omega squared, again, it's written in terms of like what I'm familiar with. So it's I omega squared. This term, I have to write it in terms of I omega divided by P1 plus 1. It is already written in that form because 0.1 is over 10, right? So I can write this as I omega over 10 plus 1. Now, given this, I know exactly where my poles and zeros are. So step 2, I determine the zeros and poles. Because I know, as soon as I determine what my zeros and poles are, I know exactly where the breakpoints are. And I know exactly at those breakpoints, I'm going to have the change in my slope. So I'm going to determine exactly like what those are. Well, I have 1 0 that's happening at 1. So I have 1 0, the 1. And I know it's a simple 0. It is a simple 0. I have 2 poles. I know 1 over squared is a pole that's happening at the origin. But since the power of it is 2, it is a simple pole at the origin, 2. Right? So I have poles at omega equals 0. That this is a second order. And if I look at this term, that tells me exactly like when my pole is. The pole is happening at omega equal 10. What kind of pole is this one? This is a simple pole as well. So this is a simple pole as well. remember how we plot 20 times log 10 of absolute value. Plotting 20 times log 10 for the single expression that we have over here, right? So we have to know the 20 times log 10 of this constant as well. So we might as well just compute it and get it out of the way. So I know my constant is 10. So 20 times log 10 of this 10 is log 10 of 10 is 1, because 10 to the root number is 10. And that number is 1. Right? So log 10 of 10 is 1. So the whole thing over here is 20. Right? So I have to like add these expressions up. Right? So let's just say this is my graph. So this is like 20 times log 10, so value of h. And this is omega. Remember, my y-axis grows as a power of 10. So my points over here, they're 10 to the 0, 10 to the 1, 10 to the 2, and so on and so forth. Right? Now all I have to do is to determine what the zeros and poles are. Because remember, whatever change I have, those changes are happening exactly at those zeros or poles. Right? So let's just see where the zeros and poles are. Well, I know I have a 0 at omega equal 1. So this is my 0. But 10 to the power of 0 is 1. Okay, so that was my 0. Let's look at the poles. If I look at the pole, I have a pole at 0. But since this axis, this big axis, is growing exponentially, it's growing as a power of 10, there is no 0 on this axis, right? What I do know, however, is that since this is a pole, I know it should come from like negative infinity. And since it's a pole, it should go down. And if it was like a simple pole at the origin, it was going down by 20. But since it's like 2, it has to go down by like negative 40, right? So the way I have to like plot it then, I have to plot whatever I have as a second order, going from negative infinity all the way down. But since I have this constant, it's basically shifted by that constant. It's being added to that constant. Right? But for now, let's forget about like this second order, because we cannot put it on this axis. Let's move on to the other one. I have a pole at 10 to the power of 1. So this is my pole. Right? I'm claiming to actually plot. Keep that in mind. If I plot 10 divided by I omega squared, what I'm doing is that I'm basically coming from infinity, the slope negative 40 dB, right? And I'm going to go all the way down till I hit the next point, right? So I'm basically coming down with this negative 40 till I hit my first 0, right? But keep that in mind. Whatever graph I have, it's going to be shifted by the constant value that I have, right? And I know the constant value is 20. So this point over here must be 20. Right? Because whatever function I have, it's going to be shifted by that 20 dB. Right? Because I'm adding everything by that 20 dB. Right? I hit the zero over here. What do I have? I have 40 going down. I hit a zero, which I know it's 20 up. So what is the total slope? It's got to be negative 20. So I'm going to go down by like negative 20 till I hit the next zero pole. Right? In this case, I'm hitting another pole. I'm going down by 20. I hit another pole, which is a simple pole. So I have to go down by another 20. So what is the total? 40. So it would look like this. Right? So all these breakpoints, whether it's pole or zero, they determine exactly where the breaking points are. And at those breaking points, I have a shift, I have a change in the slope. Right? In this case, that I have a simple pole at the origin, and I'm like negative infinity, and I'm going down because it's a pole. Since my is being shifted by that constant, this value over here must be 20 dB, must be that constant value that I have. If this one, for example, was a quadratic zero at the origin, instead of going down by like 40, I had to go up by 40, right? But again, my entire function is being shifted by that constant. So this number over here must be that constant. Right? Does that make sense what's happening? Just a quick thing, like if you check your textbook, on your textbook, it's dB over sec. What it is that dB per decade. What it means is that like the increment on the x-axis is power of 10, right? So it's no different than like writing over here. Just in case if you saw it, it's exactly the same thing, right? So let's make this a little more interesting. Here's the thing. If I'm given a transfer function, if I'm given my frequency response, I can always like have like an approximation for it, right? We're going to look at the zeros and poles. I'm looking at approximate. What if I give you the approximation and I ask you to write down the transfer function? Again, I got to be able to do it, right? Because I know exactly where the poles and zeros are, and I know my transfer function can be composed into the zeros and poles. Right? So let's do a quick example. Example. Let's just say I'm given this function. This is 20 times log 10 absolute value of h. This is my omega axis. I have 10 to the 0. This is 5. This is 10 to the 1. This is 20. This is 50. And this is 10 to the 2. Right? Let's just say I'm going down by 20 till I hit this 5. I know the corresponding value here is dB. The slope here is negative 20 dB. Right? Then it becomes flat till I hit this 20. Right? At 20, I'll go down by 20 till I hit this 50. 50 again becomes flat till I hit 100. Go down by 40 dB. The question is, where does h of omega? Right? let's look at this graph. What does it tell me? If I look at this portion of this graph, what it tells me is that I'm going down from negative infinity. So what do I have? If I start from negative infinity and go down by 20 dB, I have a simple pole at the origin, right? And I know this point over here can determine what my constant is, right? What is this 0 dB linear scale? Basically, the question I'm asking is that 20 times log 10 0 dB. What is this x? X is 1, right? So x is 1. So on linear scale, this number is representing 1, right? But remember, the whole thing over here is a simple pole at the origin. So I have a simple pole at the origin. If you want to use that, that's basically this constant divided by I omega. Right? Do you agree at this point 5, the value of this function is 1? Right? Basically, if I look at the absolute value of k over omega, that equals, that must be 1. Why? Because if I look at 20 times log 10 of so value of k over I omega evaluated at 5, that must be 0 dB. Right? Therefore, k over I omega evaluated at 5, it's exactly this point over here, must be 1. Right? What does this tell me? This tells me k over omega, which is 5, must be 1. Therefore, k is 5. So this extra information that's right here, that tells me like how much I shift my graph. And that shift tells me exactly what my constant is. Right? Because remember, a constant is just a shift. It's nothing. Right? The rest is just plug and chug. It's just like very simple. We're gonna this axis and this one x-axis, I'm going to determine if it's a pole or a zero, if it's a simple pole or like a quadratic pole or whatever that is. Okay? Look at 5. What do we have at this 5? At this 5, we're going down by 20, but it became flat. What does that mean? It must have had something that was going by 20. Which when I added these two things, they cancel each other out. Right? So we have simple 0. How do I represent this simple 0 at 5? Well, it is I omega divided by 5 plus 1. Okay. Again, I got no issues till I hit the next breaking point. At this breaking point, I was going at 0 dB. Then I go down by 20 dB. What does that tell me about this 20? It just tells me it's a simple pole. So we have a simple pole at 20. I'm going to write it as I omega over 20 plus 1 inverse. It's basically like 1 over that. I don't have a lot of space here, so I'm just going to write it in terms of inverse. It's exactly the same, right? Again, I have issue till I hit this 50. I was going down by 20. At 50, it becomes flat, which means I had to have something that was going by 20 cancel out the effect of going down by 20. Right? What does that tell me about that 50? It's a simple zero. So we have a simple zero. Which I can write as I omega divided by 50 plus 1. Right? Again, that is good. Till I hit the next breaking point. This next breaking point, which is 100, what do I have? I'm going flat, and then I suddenly go down by 20, by 40. What does that tell me? It's kind of like a quadratic pool, right? So I have a simple pool order 200, right? It's quadratic. So I'm going to write it as I omega divided by 100 plus 1 to the power of negative 2. Right? What is my function then? All these things multiply. Right? Because remember, I can decompose my transfer function into its zeros and poles. And these are the zeros and poles that I have. So I have to multiply them all out. Right? Therefore, h of omega is this constant 5 times all the zeros. So I have I omega over 5 plus 1. I have this zero as well. I have I omega divided by 50 plus 1 divided by all the poles. So I have this pole, omega 20 plus 1 times I omega over 100 plus 1 squared. Okay. So this function that's drawn over here is an approximation of this transfer function. Okay? All we have to do is to look at the breaking points and determine if it's a pole or a zero. We already have. Then we know exactly what that function is. Right? Does that make sense to everybody? Let's move on and make this a little bit more circuity. Let's just talk about circuits. So, example. Let's just say I am given this circuit. This is 1/3, and voltage across it is V out. Right? The question is asking me, what is the filter that this circuit represent? Right? So the question is, what type of filter does this circuit represent? We see the question is asking you what out over V in the frequency domain. Right? Because as soon as I know V out over V in frequency domain, I can determine what type of filter I have. Right? So how do we approach this? Well, we're going to like this in the frequency domain. Right? What is the capacitor in a frequency domain? It's 1 over I omega C. Right? Again, I'm lazy. I'm not going to take 1 over I omega C. That's 1 over SC. And define S to be I omega. So, observation. This question is asking what V out of omega over V in of omega is. Right? So I'm going to draw the circuit frequency domain. This becomes V in of S. Resistors do not change, so the value remains the same. This capacitor becomes 1 over S, right? C is 1, so it's 1 over S, right? This is I omega, right? The question is, what is this V out? Right? How do we find this V out? Remember, as soon as I go from time domain to the S domain, I can treat all the elements as a resistor, right? So I can combine these two, and the result of that combined with this one. So I have these two in series in parallel with this one, right? So let's call that Z equivalent, which is 1 over S plus 1 in parallel with 1, right? How do we compute two impedances in parallel? We multiply and divide it by the summation. So it is 1 over S plus 1 times 1 divided by 1 over S plus 1 plus 1. Find the common denominator to just simplify it a little bit. So I have S plus 1 divided by S divided by 2S plus 1 divided by S. Right? This S and this S cancel. I have S plus 1 divided by 2S. Right? So what does my circuit look like then? I have this Vn of S. I have this one. This C equivalent of S. Right? Do you agree I can find voltage across this Z equivalent of S? How do I do this? I use a voltage divider. As soon as I have voltage across this Z equivalent, I know voltage across this one, voltage across this combination. Yes? They're in parallel. I know exactly what they are. If I know voltage across this 1 and 1 over S together, which is this voltage across this Z equivalent, right? Do you agree I can compute this out? Voltage across 1 over S series. I can find voltage across one of them. How? It's another voltage divider. So I can find V out. So let's do it step by step. Let's call voltage across this Z equivalent V equivalent of S. Equivalent of S is Z equivalent divided by 1 plus Z equivalent of S times V1 of S. Right? This is Z equivalent of S. I'm going to plug it in here. I have S plus 1 divided by 2S plus 1 divided by 2S plus 1 plus S plus 1 divided by 2S plus 1 times Vn of S. Right? This and this cancel. V equivalent of S becomes S plus 1 divided by 3S plus 2 times Vn of S. Right? Let's call this equation 1. Right? What is V out then? I know this equivalent of S is voltage across these two. So I'm going to another voltage divider. So I know V out of S is 1 over S divided by 1 plus 1 over S times the equivalent of S. Let's simplify it a little. So I have 1 over S divided by S plus 1 divided by S. This and this cancel. I have 1 over s plus 1 times the equivalent of s. Right? But I know exactly what this v equivalent of s is. It's this guy. So using equation 1, have s equals 1 over s plus 1 times s plus 1 divided by 3s plus 2 times the n of s. Right? This s plus 1 and s plus 1 cancel each other out. This becomes 1 over 3s plus 2 times the n of s. Right? Again, I'm not quite interested in v out. What I'm interested in is v out over v in. Right? So I know h of s is v out is divided by v in s. And that's 1 over 3s plus 2. Right? Therefore, I can just replace s by omega. Can get h of omega, which is 1 over 2 plus 3 times I omega. Right? Let's plot this quickly before we actually determine what type of filter this is. Right? How do we plot this? Well, one way is to just actually plot the magnitude. Right? And we just learned a shortcut. We learned how to approximate this. And this is a very simple function. All we have to do is to make sure this denominator is written in the form that I am comfortable with. So all we got to do is to make this 2, 1. So I have to factor out that 2. So I can write h of omega as 1 divided by 2 times 1 plus 3 over 2 pi omega. Right? What does that tell me? It tells me my constant is half. What is my pole? I have to write it 1 plus I omega divided by p. So it's 2/3. Right? So we have a pole 2/3. So if I want to plot this 20 times log 10 of absolute value of h, what is happening? Well, it should look something like this. There's that constant, which is 20 times log 10 of half, till I hit this pole, which is 2/3, which I'm going to go down by 20 dB. Okay? What kind of filter is this? It's a low pass filter, right? Because remember, like the actual low pass filter that we were getting looks something like this. Right? So it's a good approximation of that. Right? So this is a low pass filter. Right? Let's verify it. Let's just make sure the graph that we have is actually correct. How do we verify if it's a low pass filter or a high pass filter? We're going to look at the magnitude of h of omega, right? And we're going to see like how it moves around 0 and around infinity. Right? Let's see how it works. So to verify this is indeed a low pass filter, remember h of omega was 2 plus 3 omega times I. Right? So what is the magnitude of h of omega? The magnitude is 1 over square root of the root part squared, so it's 4, plus the imaginary part squared, so it's 9 omega squared. right? Which indeed looks like this red graph that I have over here, right? Now I'm going to take a look at h of omega, when omega is zero. What's happening if omega is zero? If omega is zero, this term is zero. So I have 1 over the square root of 4. So this thing is 1/2. What happens if h of omega is evaluated around infinity? Well, if I evaluate this around infinity, this 9 omega squared dominates this 4. Therefore, the whole thing over here is the same as 1 over 3 omega. If omega approaches infinity, this is 0, right? Which is indeed a low pass filter, right? So we can always like approximate our low pass filter using what we just learned, right? Any question? Let's do example. Example. Let's just say I'm given this transfer function. This is 0.1, this is 0.7, this is 2, this is 11, this is 20, and this is 90. To this 0.1, the value over here is 6 dB. From 1 to 0.7, I'll go by 20 to this. It becomes flat. Over here it goes down till it hits this point, negative 20 dB. Then it is flat till we hit this 90, which I go down by negative 40 dB. What is h of omega? Oh, look, this 6 dB over here, that's basically our constant, right? What it tells me is that like whatever graph I have is going to be carried over this constant, which is the 6 dB. So I know 20 times log 10 constant is 6 dB. Right? I can compute k, which turns out k is actually 2. Right? The rest is like very simple. I'm going to look at the breaking points and see where this graph actually breaks and if it's going up or down. The first breaking point I have is at 0.1. So at omega equals 0.1. It was flat, then it went up. What is it? It's a simple 0, right? So I have a simple 0. So I can write it as I omega divided by 0.1 plus 1. So I can write it as like 10 times I omega plus 1. Doesn't change till I hit the next breaking point, which I was going up, and then it became flat. It's like it must have gone down by 20. So what it tells me is that at omega equals 0.7, I have a simple pole, right? So this is basically I omega divided by 0.7. So it's 10 over 7 I omega plus 1 inverse. Again, life is pretty good till I hit this 2. I'm going flat, then I go down. I have to have a pole. So at omega equals 2, I have a simple pole. I can write it as I omega over 2 plus 1 to the power of negative 1. Again, life is pretty good till I hit this 11. Going down by 20, then it becomes flat. It's like I must have had something that was going up by 20. Right? What does that tell me about 11? It must be 0. And since it was going by 20 and it became 0, it means it's just a simple 0. It's order 1. Right? So at the equals 11, I have a simple 0, which I can write it as I omega divided by 11 plus 1. Again, life is good till I hit 90, which I go down by negative 40. What does that tell me? First of all, it's going down, so it must be a pole. And since it's going down by negative 40, it must be quadratic. It's like the second order. So I know at the equals 90, the simple pole of order 2. So I can write it as I omega over 90 plus 1 with power of negative 2. Right? What is my h of omega? Multiply all of them. Right? So my h of omega is, well, I have the constant. I have all the zeros plus 1. I have another 0 over here. Another 0. And then I have my poles. I have 10 over 7 I omega plus 1. I omega over 2 plus 1. And the last one, I omega over 90 plus 1 squared. Right? So it's very easy. I only need to determine where the zeros and poles are. Right? Any question? Let's do interesting example as well. Example? Let's just say I have these two circuits, V in Ft and L, and voltage across this is V out. And I have another circuit this time voltage across this is V out. And the question is asking me determine what type of filter each circuit is representing. So determine what kind of filter these are. Right? Yeah, let's just assume this is I omega. I don't want to keep writing I omega. Right? How do we analyze this? How do we know what type of filter it is? We're going to have to take it to the frequency domain and start analyzing the frequency domain. Right? If I have an inductor in the frequency domain, my inductor becomes I omega L. So I write it as SL. Right? So the circuit becomes V input S. Resistance does not change. Inductor becomes SL. I need to find V out of S. In this circuit, again, it's the same thing. Inductor becomes SL. Resistance would not change. I need to find V out of this. But remember, these two circuits are very simple circuits. Why? Because as soon as I go from time domain to S or omega domain, I can treat all the elements that I have as a resistor. So what are these circuits? This is the voltage divider, right? So I can compute V out of S. In this case, it's SL plus SL times V in of S. In this case, out of S is R divided by R plus SL in of S. Again, I'm not quite interested in V out because I want to determine what type of filter I have. So I need to look at V out over V in, right? But that's not very difficult. Given this, I know h of s is SL over R plus SL. Again, I can replace S by I omega. I write h of omega. In this case, it is I omega m divided by R plus I omega m. In this case, h of s is R divided by R plus SL, which tells me h of omega must be R over R plus I omega L. Right? To determine what kind of filter they are, I'll have to look at the absolute value of them. Right? So what is the absolute value of this one? Well, that's absolute value of the numerator, the absolute value of the denominator. What is the absolute value of I omega L? It's omega L, right? Absolute value of I is 1. So that is omega L. Absolute value of the denominator is the square root of the real part squared plus the imaginary part squared. So square root of R squared plus omega L squared. Right? So to determine what type of filter it is, I have to look at this when omega is very small, omega is very big. So what is it? What is h of omega when omega is 0? If omega is 0, the denominator is 0, so the whole thing is 0. Right? How about the value of h of omega when omega approaches infinity? The denominator is dominated by this omega squared L squared square root. So it would be omega L divided by omega L. So it would be 1. What type of filter is this? It's a high pass filter. Right? How about this one? Well, if I look at absolute value of h of omega, that is R divided by square root of R squared plus omega L, the whole thing squared. Right? Again, I got to know what it's like around very low frequencies and very high frequencies. So if I look at h of omega, omega is 0. So I have R divided by square root of R squared. This term is 0. Right? So this is 1. And if I look at the absolute value of h of omega when omega approaches infinity, again, this omega L squared dominates this R squared. So it's R over omega L. That approaches infinity. So the whole thing over here is 0. Right? What kind of filter is this? Let's say low pass filter. Right? Let's just try to plot this using this method that we actually just learned. Right? So I know h of omega is I omega L divided by R plus I omega L. Well, the numerator is pretty good because I know I have a 0 at the origin. Right? So I have L times I omega. Denominator, I don't like this R. To make this 1, so I'm going to factor it out. So I have R times I omega L over L plus 1. Right? This one is quite easy. The numerator is simple. It's R. The denominator, again, I don't like this R. So I'm going to factor it out. So I have 1 plus I omega L over R. Right? What is my constant here? Well, obviously, my constant is L over R. Right? So my constant here is L over R. I have a 0 at the origin. So I have a simple 0 at the origin. And this term over here tells me I have a simple pole at what? L. Right? I have to write it as omega divided by P. So I have to take this L to the bottom. So I have a simple pole at L over L. Right? So if I plot it, what does it look like? Well, I have a simple zero at the origin. It's I'm going to go from negative infinity by 20 dB. So it would look something like this. Right? And then I have a pole, keeps going up till I hit my pole at this R over L. Right? I'm going up by 20 dB. I hit the pole that's going down by 20 dB. So what's happening over here? It becomes flat. Right? Which is indeed a high pass filter. Right? This one, K is 1. Don't have any zero, so we have a pole at the L. So if I plot this 20 times log 10 of the magnitude, I only have pole that's happening at this R over L. So it was constant till I hit this pole, and it goes down by 20 dB, which is indeed a low pass filter. Right? Any question? Does that make sense? See you guys Monday.